Hello and welcome to this lesson. So in today's lesson, we are going to look at the atomic structure. So atomic structure in line with the quantum numbers. So for today's lesson, our main objective is to understand the shapes of atomic orbitals. So let's quickly dive into the lesson. So we'll start by looking at the Bose model of an atom. So the Bose model of an atom demonstrates to us that we have the central part of an atom, which is the nucleus. Then we have different energy levels. So each electron will be found in different energy levels, which are also known as shells. So we can find an electron here in the first energy level, we can find an electron in the third energy level, we can find an electron in the third energy level, and the only difference there is that those electrons so we say electron 1, electron 2, electron 3. So electron 1, 2 and 3 will have different energy levels. So according to atomic quantum theory, we focus on the behavior of electrons inside an atom. So for us to understand the behavior of electrons inside an atom, we look at the 4 quantum numbers. The 4 quantum numbers. The first one is known as the principal quantum number. The principal quantum number, which is denoted by n. So the principal quantum number just describes the energy level, and the size of that which an electron occupy. So the energy level that is occupied by that particular electron. So the emphasis is that this energy level is always above 0. So it's a positive integer, and it varies from 1, 2, 3, 4, 5, 6, 7, considering the electron in the ground state. This is what is important, or this is the most important information that we have to know about a principal quantum number. So it tells us the energy level that an electron occupies. And once we have an understanding of the principal quantum number, then we can look at the second, which is known as the angular quantum number or the azimuthal quantum number. What does this focus on? So this obviously is denoted by small letter L. So this describes the shape of the atomic orbitals. So there is a relationship between the principal quantum number and the angular quantum number, and the relationship is that n is less or equal to, so L is less or equal to n minus 1. Therefore, if n is equal to 1, then using that formula we can say L is less or equal to 0, which means that L is 0. When n is equal to 2, then it means that L is less or equal to 1, which means that L can be 0 or can be 1. When n is equal to 3, is L less than 2, which means that L can be 0, 1, or 2. Then when n is equal to 4, means that L is less or equal to 3, which means that L can be 0, 1, 2, 3. So 0 in terms of shapes, 0 represents the s orbital, so that is s, then 1 represents the p orbital, so that is s, p, then 2 represents the d, then this is s, p, d, f. So those are the respective sub levels. So these are called sub levels. So this is the relationship between the principal quantum number and the angular quantum number. Now, how can we relate this to configuration or electronic configuration, which we're going to look at in the next video? So we have 1s, we have 2s, 2p, we have 3s, 3p, 3d, then we have 4s, 4p, 4d, and 4f. It's impossible to have a 1p. Why? Because in the sub-levels we only have 0. It's impossible to have a 2d, because when L is less than or equal to 1, we can only have those 2 sub levels. Then the SPD represents the atomic orbitals. Now, can we focus on the shapes of these atomic orbitals? shapes of atomic orbitals. So when L is equal to 0, we're saying this is S. Then in terms of shape, S is denoted by spherical. So this is along the Z, the Y, and the X axis. So this is called spherical. Then when L is less or equal to 0, we said we have 1s, 2s, and 2p. So we know the shape of the S, we want to know the shape of P. So for P, when we go to the third quantum number, which is the magnetic quantum number, denoted by M sub L, this focuses on the orientation. Now here, the relationship between the angular quantum number and the magnetic quantum number is this. So meaning, if your L is 0, then your ML is 0. But if your L is 1, then your ML is -1, 0, 1. If your L is 2, this is -2, -1, 0, 1, 2. And then we'll realize that here, that is where the P is, then this represents the D. So it means that we have 3 orbitals in this sublevel, where those 3 orbitals are Px, Py, and Pz. Then in terms of shape, that is for P orbital. So we said we have the Px, Py, and the Pz. So when we draw this is our Z axis, this is our Y, this is our X. So if we're looking at the Px will be along the X axis. Then if we're looking at, this is Y, sorry, and this is X. If we're looking at the Py, then our orbital will be along the Y axis. Then if we're looking at the last one, which is, sorry, Z, X, Y. So this is going to be along the Z axis. So this will be called PZ. So these are the 3 sub levels. So this is, we are in the 2p. So this can be 3, which is -1, 0, and 1. Then all these 3 orbitals can be any of these given 3. Just look at the shapes of the d orbitals. So the d orbital, so for the d orbital, when we say L is equal to 2, then the ML is going to be -2, -1, 0, 1, 2, meaning we have 5, 1, 2, 3, 4, 5 orbitals. So in terms of shape, they are a bit complex. So let me start with the first one. So if we have this, y, x, z, we'll start with what we call the dyz. So for the dyz, they're going to be like this and this. So that's a dyz. Then z, y, x, we have the dxy. So the dxy is going to be along this and then here. The dxy, then y, x, then we have what we call the dxz. So the dxz here, and then here. So those are the three. So we have the dyz, dxy, the dxz, then we're remaining with the dx squared y squared, then the dz squared, which appears like this. So this is x, this is z. So the dx squared y squared is along the y and along the x. Then the last one, which is along the z axis, which is the dz squared, appears like this. Then we have something like this. So they appear to be a bit complex and we're not supposed to know them. The shapes obviously, but we have to know the names of the orbitals. So for the d we have 5. Then we have the f. Let me do this. We have the f orbital, which is more complex, but these are supposed to be 7. These are supposed to be 7. 3, 4, 5, 6, 7. So here we have the 4s, the 4p, the 4d, and the 4f. So these are supposed to be 7 sub levels. Then the last, which is the 4th, is the spin quantum number. The spin quantum number, denoted by m sub s. So this just focuses on the spin direction of an atom, and there are only 2. So it's either an up spin direction, which is denoted by positive half, or a down spin direction denoted by negative half. So that's it for today's video. See you in the next video.